Okay, so we're on to question 10, and question 10 gives you some data and it asks you to plot the velocity time graph. Now, straight away, let's be clear that with a velocity time graph, you must put time on the x-axis, okay, and you must put velocity on the y-axis, okay. So I've got my axes the right way around, okay, and I've labelled them up with the quantity and with the units. Then I'm going to look at I'm going to look at time first. I'm just going to see what fits here. Okay, so if I go, maybe that's 0, 10, 20, 30, 40. Oh, that's not going to fit on my graph. Okay, so I'm not going to come up with some crazy scale where I've got to divide by 7 or anything like that, right? Okay, just if it doesn't fit, then just divide by 2, right? So now instead of going up with 2 big squares is equal 10, I'm going to go up with 1 big square is equal 10. So that's going to become 10, 20, 30, 40, 40, 50. So I'm still using a sensible scale that doesn't require any ridiculous calculations to try and work out, how to fit it onto the scale. And it fills up more than half my graph paper along the x-axis. And that's the key thing, right? If it doesn't fill up half the graph paper, then just double it. Okay, if it's more than the graph paper, then just halve it and just keep doing that until it fits, right? Going to use the same trick. Okay, I need to be able to go up to a maximum of 21 on my y-axis, right? Okay, so I'm just going to 4 big squares as 10. Is that going to work? All right. If I did 2 big squares as 10, then that would be 10. That would be 20, and then I haven't filled up half my graph paper, have I? So that's not good. All right. So I'm going to double my scale. So that's going to become 5. That's going to become 10. This is going to be 15. That's going to be 20. Okay, and I've got 25 at the top. Okay. So that's perfect. I'm going to be able to fit all of my points on there, right? So now we've got 10. On the point is at 10, 8. Okay, and now I've got to remember each of these 2 small squares is worth 1, right? Okay, so that's where 8's going to be. You've got to be correct to the nearest half a small square when you're plotting these. So you do have to be careful, and you do have to think carefully about what scale you've gone with, right? This one is 14.5. Okay, if 2 small squares is equal 1, then 1 small square is equal a half, so that's in the right place there. Okay, and then 18, and then finally 21, like that. There we go. Okay, so my graph's nearly finished. Okay, but I do need to draw a straight line through all of my points. Okay, line of best fit. Okay, now you'll notice it doesn't go through 0, 0. And that's important because if you look back at the data table, at no point in the data table does it say that it goes through 0, 0, right? So don't force it to go through 0, 0 if that isn't a point on the graph. Okay, so my scale's sensible, my axes are labelled, and I've got units, that's worth 1. All of my points are plotted correctly, that's worth another 1. And my line is plotted correctly, that's 3 out of 3. Happy days. So how does the graph show that the velocity's got a constant acceleration? Well, think about the formula for acceleration. It's the change in velocity over the change in time. Okay, which is interesting, isn't it? Because, velocity's on the y-axis, all right, and time's on the x-axis. Hold on, delta y over delta x, that's the rise over the run. That is the gradient, right? So the gradient of this graph is the acceleration. So if it's got a constant acceleration, that must mean that it's got a constant gradient. Is that true? Yeah, it's a straight line. It's got a constant gradient. Okay, it's a straight line. Yeah, okay, that's it. So how can you tell? It's because the gradient of the graph is constant. Calculate the acceleration of the lorry, right? So there's 2 ways of doing this. You can either do delta v over delta t, or you can do rise over run. If you're going to do rise over run, then you choose the biggest possible triangle to do it across. Okay, and it's that triangle there. All right. So if you look back at the original data, then that's going to give you a base of 40, okay, from there to there. That's your run, and then your rise is 21 minus 8, which is 13. Okay. So you can do gradient is rise over run, which is 13 divided by 40, okay, which gets you 0.325, okay. Or you can do acceleration is the change in velocity over the change in time, and it's exactly the same substitution. Okay, from the data table you can see that the velocity has increased by 13 when the time increased by 40. That's it. End of the questions, end of the paper.